Welcome. Today's notes worksheet is entitled Graphs of Polynomial Functions Day 1. We'll do a few investigations today, setting up some of the graphical characteristics of polynomial functions. We'll do some very general investigations, and then we'll probably dive in and look at some of the more specific characteristics. So why don't we go ahead and start with what's at the top of your page here. The investigation reads, what do the top 3 graphs have in common that differ from one or more of the bottom 3 graphs? So we're going to have to draw these in by hand here. So what I'm going to need you to do is draw 6 coordinate planes. Let's do 3 on top. So something like that would do. And then right underneath, if you would please, let's do 3 down below. And I'm going to draw the graphs of 6 functions in just a moment here. So let's get that together. On the top, when I draw the graphs of my functions in these 3, they would be very characteristic of a polynomial function. And then when I draw these 3 down below, they're not going to be representational of a polynomial function. And so what I'd ask is, what do the top 3 have in common that the bottom 3 do not? All right, so let's get this started here. Let's do something like this initially. There we go. That could be a polynomial function. Let's do something like this right here. Here's a secondary one. Looks good. Also would be characterized as a polynomial function. And let's see, maybe the third one over here, something like this, give or take. Doesn't have to be perfect by any means. And those 3 graphs, again, would sort of fit the characteristics of polynomial functions. Now, what I'd like for you to do is see if you can think about any commonalities that they have, and especially how they'll differ from the bottom 3, which I'm going to draw here as we go through it. So let's do this one first. Let's do the V shape. So that would be sort of the absolute value family. Let's do this one right here. Something like this. This would be in the rational family. And something like this potentially. I'll do like a piecewise function, something like this. There we go. Looks pretty good. So again, top 3 characteristics of polynomial functions. Bottom 3 different families. And the question is, what do these 3 have in common, obviously, that differ from one or more of these down below? All right, so maybe pause the video and stare at them for just a second and see what you think. But what we want to do is just come up with some very basic characteristics of those polynomial functions from the top. And then as you can see, there's a little conclusion down below here. So let me go ahead and read that as you guys are thinking it over, and then we'll go ahead and write a couple things in. So it says, graphs of polynomial functions are something, and it's a word that we use quite a bit in the mathematics at this level and some levels above, and have, and then we want to fill in that piece right there as well. All right. Well, I guess here's what I would say. These 3 differ from these 2 in a very particular way, and that's what I'm thinking about in that first blank. And if you notice when I drew these graphs, I never really had to pick up my pencil. I just drew all the way from start to finish, just drew it all the way. Whereas if I had to draw the function here, I would have to pick up my pencil. So here I draw this piece, and then I have to pick it up to draw this piece. And so these 3 are all what we would call continuous. And again, continuity is something that you'll explore in a little more detail at some of the next levels. But that would be the idea. For every polynomial function, they are continuous. All right, and you can see that right here. Obviously, this one as well. Had to pick up my pencil in order to draw that graph. Discontinuous here and here. Okay. Now, let's see how these 3 would potentially differ from this one right here. So as I said, this is the absolute value family. These are polynomials and kind of fit that mold pretty well. And the question is, of course, what is that difference? Well, look at the max and min, or really the corners, so to speak. You see how nice and smooth they are and rounded they are on these? And then look at the absolute value. Look how abrupt and straight that is. And so that's the idea. They have, I don't know how to necessarily word this. I'm going to write it as rounded corners. They're not sharp corners, not abrupt. Hopefully you kind of get that idea. And again, when you do some work at the next couple levels there, you really start to look at that in good detail. But those maxes and mins are a little more smooth and rounded as opposed to abrupt and sharp. Okay, good. So I think we'll kind of use this idea, especially the continuity as we go through the process, but kind of get your mind around these graphs right up here as opposed to something like these down below. All right, let's move it along. So we've got a nice couple questions that we'll get into here before we get into some of the specific characteristics. And I guess if you've been kind of paying attention here a little bit, you can probably answer this question right there. So as a result of what we answered in that conclusion, what is the domain of every polynomial function? Remember, domain, think horizontal. And remember, if I don't have to pick up my pencil to draw it as I move left to right and just keep going forever and ever and ever, I hope you would agree with me that the domain of every polynomial function is going to be all real numbers. That would be the case. And obviously, sorry for going back and forth here, but obviously this one, there is a discontinuity, and so there is a number excluded from the domain. Okay, good. Next piece, and I guess we want to get into a few more of the details of these polynomial functions. What families of functions encompass polynomials? Well, if you remember what we kind of talked about way back when, a linear function is a polynomial. Degree 2, a quadratic function is a polynomial. A cubic function, degree 3, is a polynomial. A quartic function, so x to the 4th, degree 4, that would be a polynomial. Quintic, degree 5, x to the 5th would be a polynomial. And then degree 6, degree 7, etc., etc., etc. So as we kind of think about, all right, well, what does a polynomial represent? Well, we've actually explored these already. We've looked at linear functions. We've looked at quadratic functions. And again, those all encompass polynomials. Okay, good. All right, and by the way, just as we look at this, every linear function that we can draw is going to be the domain of all real numbers. Every quadratic has a domain of all real numbers. So we've seen these in action already. I don't know if we've necessarily put it together in these words, but essentially all of these functions, the domain is all real numbers. All right, let's move forward. Next piece on your paper, it says every polynomial defines a function. Absolutely. And any value of x for which f of x equals 0, so when the output is 0, that's the key here. In fact, you might want to write that. Output is 0. That's what we mean here. Of course, f of x is just a fancy way to talk about y. So when the output is 0, so any value of x for which f of x is 0 is what is called a 0 of the function. And we'll be looking a lot at the zeros of functions as we go through our curriculum here. And so why don't we go ahead and start out with example 1 based on exactly this premise. All right, so got 2 parts for example 1, and the algebra here shouldn't scare us. But let's go ahead and see if we can put this together within the context of what we just talked about above. So example 1, find the zeros of the functions, and I've got this nice little cubic right here. Again, polynomial, of course. X to the 3rd, so it is cubic. And the idea is to find the zeros. Well, again, what we want to do is solve for x when the output is 0. So we're going to put the output in as 0 right there, and then x cubed minus 5x squared and plus 4x. And that, of course, is an equation that we are capable of solving. The means that we have solved it before have been through factoring primarily. And so we'll go ahead and try that out right here. And so want to just refresh your memory here. Let's see if we can factor this a little bit. So I see these 3 terms all have an x in them. And so I'm going to go ahead and take out the x there and get x squared minus 5x and then plus 4 when I do that. That looks pretty good. And of course, I can go a little further on that quadratic. So I'm going to go ahead and do that. Get my 2 binomials set up. And again, really not too bad. X and x. Hoping you agree, minus 4 minus 1 would do the trick there. And what I've done is taken this function in standard form and manipulated it into factored form. And this is obviously a good position to be in. We've talked about this before, where I have factors set to 0. And what that means is if any of these factors are 0, then it makes the entire quantity equal to 0, and hence it would balance the equation. So what would make x 0? What would make x minus 4 0? What would make x minus 1 0? And again, I hope you all agree with me that we would get these three values when all said and done. All right. These would be considered the zeros of the function. Okay, so any values of x that would make the output 0. And just real quick before we get into letter B, if I put 0 in for x and calculated, what would we get, everyone? 0. If I put 4 in for x, what would we get? 0. And if I put 1 back in for x, what would we get, of course? 0. Great. We're going to graph that example in just a second. Let's go ahead and do the algebra for part B, and then we'll come back to that example 1A in just a sec. All right, guys, why don't we repeat the process one more time over here? Yeah, not too bad. So the idea is to find the zeros. We're going to set that function. We're going to set the output to 0 there, and then solve for x. This one looks like it is a grouping approach, just from what I see. So just a refresher on grouping. And let's go ahead and take out an x squared from each of these, if you remember how this works. Take out the x squared, and I get x plus 3. Oh, this one right here, not too bad. I'm going to take out the negative 25, of course, which would give us the x plus 3. And of course, that setup allows us to go ahead and factor this by grouping. If you remember correctly here, in this part and in this part, separated by that minus, I do have a greatest common factor of x plus 3. So if you remember correctly, we take out the x plus 3 from this and from this. And when I do, I get x squared from this end. Here's my minus. And I get 25 from this end. Looks great. I think we can go a little step further. Remember, we talk a lot about factoring. It's recognizing the pattern and then applying the pattern. And so I see a difference of 2 squares right here. I hope you recognize that as well. And so I'm going to go ahead and factor that. I have x plus 3 from this. And how does x plus 5 and x minus 5 sound right here? So again, good position to be in. Factors set to 0. We'll see that a lot over the course of our curriculum. And once those factors are set to 0, what would make each one of these factors 0 makes the entire quantity 0. And I hope you would agree. I'm going to go ahead and bring this on up. It looks like we get x equals negative 3 from that first one, x equals negative 5 from the second one, and x equals 5 from the third. And as a result, I've got my 3 zeros. Sorry for repeating myself on this end, but just remember what that means is if I put negative 3 back in for x, it would make the output 0. Negative 5 in for x makes the output 0, and 5 in for x makes the output 0. Those are the 3 zeros of the function. Excellent. All right, so a couple of conclusions to be drawn here. We're going to graph momentarily, but I think I can do the conclusion number 1 without the graphing piece. So I guess the connection to be made, and we'll be making it a lot in the near future, is seeing the connection between factors and zeros. So especially this end right here, if x minus 4 is a factor of the polynomial, well, then 4 is a 0. If x minus 1 is a factor of the polynomial, 1 is a 0. If x plus 3 is a factor of the polynomial, negative 3 is a 0. So zeros come from the factors. Okay, so that's exactly what I'm going to put right up here. If x minus c is a is a factor, let me word that correctly for you. There we go. So if x minus c is a factor of the polynomial, then c, we'll talk a lot about the c value as we talk more about zeros. So if x minus c is a factor of the polynomial, then c is a 0 of the function. Factors and zeros. And even on this end, guys, so I already alluded to this one. So think of this as like x minus negative 3. That would be another way to talk about x plus 3. So if x minus negative 3 is a factor, negative 3 is the 0. If x minus negative 5 is a factor, then negative 5 is a 0. If x minus 5 is a factor, 5 is a 0. So factors produce the zeros. Perfect. All right, now let's bring up that graphing calculator. So what I need us to do is just very simply go to the y equals, and it does say graph the function from example 1 on the calculator. Let's just do the 1a. I don't think we have to do the 1b here. And what I want you to do is graph this into the y equals, and then focus on these three numbers and see where you find them, where an x value is 0, x is 4, and x is 1. See if you can locate those, 0, 4, and 1. All right, so I'm going to go ahead and do this as well. Let's get this moving. So I've got that piece right there, and plus 4x will do. Zoom standard should be just fine for this. And so again, take a look at the graph. There's a nice cubic. And by the way, notice it's a cubic graph. Domain is all real numbers. There's the continuity that we talked about. There are the rounded corners. It looks like it has a max up here and a min down there. That looks really nice. And again, what I want you to do is focus on where you see x being equal to 0, x being 4, and x being 1. And notice where they show up exactly on the coordinate plane. There's x is 0, there's x is 1, and there's x is 4. And if you notice, each of those x values would be an x-intercept of the graph. And that's exactly the connection to be made between our zeros as real numbers here showing up on the graph. And that makes sense if you really think about this, because we're making y equal to 0 and then solving. Well, graphically, what do we know about when y is equal to 0? Well, that's on the x-intercept. So when y is 0, we've got that. When y is 0 and when y is 0. 3 different x values that make y 0. Perfect. Let's get our conclusion in. So in this case, here's what I would say. If c, and again kind of our c value, that's what we'll call these, if c is a real 0, and we'll be seeing all types of zeros as we explore this in more detail, if c is a real 0 of the function, then it is an x-intercept on its graph. And we'll use that idea as we, again, try to find different types of zeros for all different types of polynomial functions. We're going to look at quadratics, which we have, cubics, quartics, we'll even look at quintics. We might, as the curriculum progresses, even go into some degree 6s, maybe just even a degree 7. We'll see. Okay, let's move forward. So first graphical characteristic that we looked at would be the zeros of the function. The second graphical characteristic, and the phrase kind of speaks for itself, is what's called the end behavior. So it's the behavior of the graph on its ends, on the outskirts of it. And we're going to be pretty straightforward with this, not too detailed, not too formal. We're just going to use the terms rise and fall. And I'll show you exactly what we mean here momentarily. I've got a beautiful looking table here to get us set up, and we'll see what it produces. So there's a reason behind all of these right here. There is some coherent rationale for all that stuff. So let's put this in play. And if you notice, I've put all the families that we talked about. A couple linears, a couple quadratics, a couple cubics, a couple quartics, a couple quintics. So degrees 1 through 5, everyone. Let's get those going. Didn't need to do any more than that. So guys, fill them in. Degrees 1, 1, 2, 2. I'm just going to see if I can line myself up all right here. 3, 3, 4, 4, and 5, 5. So 2 of each. And again, there is a reason for doing that, as you'll see momentarily. And not only are we going to explore the degree, but one more piece to the puzzle will be what's called the leading coefficient. In standard form, that would be the number all the way on the left there. outside the leading term. So positive 3, negative 1, positive 3, negative 2, positive 6, negative 1, etc., etc. I'm hoping everybody sees that leading coefficient right here out in front of the leading term in standard form. All I care about, everybody, is positive versus negative. I'm going to shortchange this a little bit, and you'll notice that they alternate. First one's positive, second one's negative. And the idea is you can look at any polynomial function in standard form, and just based on its degree and leading coefficient, you'll be able to tell me the end behavior in a matter of seconds. So what we want to do is just explore a couple of the patterns here, see if we can fill that out. And you'll see a little table below on your sheet here to kind of put it all together. So again, all you need is the degree and the leading coefficient for any of these, and you'll be able to identify the rise and fall of the graph. All right, so there are two sides of the end behavior that we're going to be looking at, of course. There's left end behavior and right end behavior. A little more formally, what this would mean is we're looking at what happens to the graph as x approaches negative infinity. So what happens as we go to the left on the graph? X gets further and further and further into the negatives. And so that's what we mean. As x goes to negative infinity, what's going on with the graph? This one, of course, is as x approaches infinity. What happens is as x gets larger and larger and larger, that would be going to the right on the graph. And so what we're going to do is just graph a few of these. I'm going to graph a few and then ask you to pause and then graph a couple on your own and then maybe fill in the table. So let's go ahead and grab the calculator and let's do the top one. So basically y equals 3x minus 1. All right, so I'm going to go on back and I'll tell you exactly what we're looking for here. If you're not sure, that's all right. Give it a moment. So there is our linear function. It is a polynomial. And of course the question is, here's my line by the way, what's going on with this graph on the end behavior that is to the left and the end behavior that is to the right? So I hope you would all agree with me, of course, that this is a line. And so what that means is as I focus on this graph going to the left, being a line, it's just going to keep going and going and going forever and ever. It's never going to turn back, right? In fact, I'm tracing it as best I can right here. It's going forever and ever and ever. So as we go to the left, everybody, does it seem like my graph is rising or falling? Well, it looks like it's falling. The function values are getting smaller and smaller and smaller as we go to the left. I hope that makes pretty good sense. So we would say the left end behavior is fall. Now as I look at the right end behavior, well again, that's kind of tracking it there. There's a line. It's never turning back, so it's just going to keep going and going up and up and up as we go to the right. So it's falling to the left and it's rising to the right. And so without a whole lot of issue, guys, fall, rise. That's how we would read the end behavior from that graph. Fall, rise. Cool. Again, let's do just a couple more. I'm going to skip around a little bit just so you can see. I'm going to do the fourth one, everybody, the fourth one right here. So this quadratic with the leading coefficient being negative. So degree 2, leading coefficient is negative. And again, once you get the hang of it, the idea is all you need to do is see that piece, and you'll be able to tell me the end behavior literally in a second or two. Okay, so negative 2x squared. I've got my plus 4x. How about plus 3? I'll hit graph, and there we go. So end behavior. We've got a nice looking parabola right here. And here we go. As I follow it to the left, do you see what's going on with the function values? They seem to be going smaller and smaller. They're going lower and lower. The y values are shooting towards negative infinity as the x values are shooting towards negative infinity. So the graph is falling. And as I go to the right, because it's a parabola here, the end behavior is the same, and so it's going down and down and down forever and ever and ever. Hope you would agree as we go to the right, one more time, the graph is falling. And so as a result here, we would call the end behavior, very simply, fall, fall. All right, you've got me for one more, and then you've got to fill it in yourself. Let's see, I think I will do, how about the last one? Let's see if I can get that in. What's kind of fascinating about this piece, in my opinion, is as big and comprehensive as this cubic is, all that matters is the degree and the leading coefficient. All this stuff behind it is actually irrelevant. All right, so I'll go ahead and type that in. This one's going to take a little while, but all right, let's get there. And got that. Looks like I've got an x cubed. Come on, a little faster. X squared and plus 1. All right, hopefully I got it. And again, all that matters is the degree, degree 5, leading coefficient, negative. Okay, so we've got a couple turning points in there. Notice graph's coming down, comes back up, comes back down. And this sort of gives the highlights of in the middle, but really on the outskirts, at the end, do you see that this graph, as we go to the left, is just going to rise and rise and rise forever and ever and ever. Good. Not turning back. The turning points have already occurred. And over here, as I go to the right, I'm hoping you see that turning points are done, so this graph is just going to fall, fall, fall forever and ever. So left end behavior is rise, right end behavior is fall, and that's exactly what we would say. Rise, fall. All right. So that's what we're looking for. I did 3 out of the 10. Be great for you to maybe at least graph a couple more, give or take. I'll leave that up to you. I'm going to ask you to pause the video for a second and write some more in, and then I'm going to fill in the table the way it should be and then see if we can come up with a couple conclusions. All right. Well, let's see how you did. Degree 1, negative leading coefficient, should be rise, fall. Degree 2, a parabola with a positive leading coefficient, should be rise, rise. Okay. Degree 3, leading coefficient is positive, should be fall, rise. Degree 3, leading coefficient negative, then it turns into rise, fall. Kind of interesting. Fall, rise, then rise, fall. Degree 4, maybe, just maybe at this stage you could start to see, even without graphing them, what it may be. But degree 4 positive is rise, rise. Hey everyone, degree 4 negative, what would you think? Fall, fall. Very cool. One more for me to take care of. The quintic. Positive leading coefficient should be fall, rise. Beautiful. And so that's pretty much it. Just these pieces alone. Degree, leading coefficient, and you could tell me the end behavior. Well, let's fill in some conclusions. So let's do this, I suppose. These two kind of going together nicely. And then really they're just 4 scenarios. So just kind of remembering, so to speak, or picturing the 4 scenarios is exactly what's on tap for you. Okay, so let's see. For polynomial functions of odd degree, so just odd versus even at this stage, what did you notice about the end behavior? Odd versus even. See if you can fill in 1 or 2. Be cool to see. I'm going to go on back. Sorry, there we go. What did you notice about the odds? Boom, there, and there. Okay, well, I hope you noticed. Sorry, wrong direction there. Let's get that going. For polynomial functions of an odd degree, the end behavior of the graphs is different. They're opposites. One is rise, one is fall. Whereas I hope you noticed for the evens, the quadratics, the quartics, degree 6, if we did that, they would be the same. Either rise, rise, or fall, fall. So now let's just get a little more specific with the 4 scenarios that we would see. And let's draw maybe a couple things in off to the side as well. So if the degree is odd, again, as soon as you hear degree odd, it means it's going to be different end behavior. Leading coefficient's positive, then what we basically had was a fall-rise situation. Fall to the left, rise to the right. The way I think of this, everybody, if it's odd and positive leading coefficient I always think of as increasing. And we always kind of read a graph left to right. And so do you see this would be an increasing graph overall, even though it's got intervals where it's decreasing? Basically, on the whole, it's increasing. So positive, it's going upward as we go left to right. So fall, rise. Cool. If the degree is odd and the leading coefficient is negative, then the graph, it's rise, fall. So you could put that in grammatically correct there, rises and falls, but basically that's what I would say. It's a rise, fall, and behavior. And same thing here, something like this would do. And when I think of a negative leading coefficient, I think of decreasing. And so ultimately what's going is sort of like that. Left to right, it's decreasing. So left end behavior, right end behavior. Perfect. Let's fill in the last two. If the degree is even and the leading coefficient is positive, it's going to be rise, rise. Again, put that in a little more grammatically correct if you could, but it doesn't matter to me. Rise, rise is what we're looking for. And so it might look something like this. That looks great. Rise, rise. And again, positive, think like it's going upward. And last but not least, degree is even, leading coefficient is negative, so it's going to be fall, fall. And so something like this, just sort of the flipped version, so to speak. And there you have it. And those are the only four. Again, that's what we'll see. Odds, evens. Beautiful. All right, take a look at that. See if it all makes pretty good sense. Feel free to ask a question on your graphing calculator if you have it. But basically that would be the scenario for this particular pattern. And let's move on to the last investigation. So the last investigation today is on multiplicities of zeros. We've already talked about zeros a little bit. And same thing, we're going to be very informal about it, just talking about touching the x-axis and crossing the x-axis. So remember, zeros show up as x-intercepts. And so we're going to kind of look at that in a little more detail. Now, unlike the last investigation, everybody, I wrote these polynomial functions not in standard form, but I factored them for you. And because we already talked about this on the front side, remember zeros come from the factors. And so we'll put that together momentarily here. I think we'll do the first column and the second column, and then we'll graph it up and wrap this up here. So here we go. Zeros come from factors. So if x minus 1 is a factor, then 1 is a 0. If x plus 2 is a factor, or think of this as x minus negative 2, so negative 2 is a 0. If x plus 4 is a factor, negative 4 is a 0. Those would be the three zeros. Since they are all real numbers, they will show up as x-intercepts on the graph momentarily. Okay. X plus 3 is a factor. In fact, it's two factors of x plus 3 because it's squared. Negative 3 would be a 0, and 2 would be a 0. This is a good one. If x is a factor, what's the 0? 0, yeah. And actually, it comes from two factors of x. That's kind of cool. And 4 as well. Here, guys, it looks like negative 2 would be the 0. Actually, it comes from three factors of it. X plus 2 times x plus 2 times x plus 2. All right, and last but not least, negative 4, 2, and 4. All right, so good connection to be made. Zeros come from those factors. Now the multiplicities, and this is basically how many of the factors did our 0 come from. And in this case, I hope you would all agree, this top one, there's only one factor of x minus 1. There's only one factor of x plus 2. And there's only one factor of x plus 4. So we would call these singles zeros. So I'm just going to write singles by them. Whereas, here's a subtle difference, the negative 3 that we had from here came from two factors of x plus 3, right? Officially, x plus 3 squared means x plus 3 times x plus 3. So we would call that negative 3, lo and behold, a double. But the 2 is still a single because it only comes from one factor of x minus 2. All right, now we're rolling with it. The 0 comes from two factors of x. The 4 comes from 2 factors of x minus 4, both doubles. This one's a triple, of course, because it comes from 3 factors of x plus 2. And then we see here, this would be a triple, a double, and a single. All right, not too bad. Let's go ahead and graph this on the calculator, come up with our quick conclusion, and we'll obviously pick up some remaining pieces and do some examples on the day 2. All righty, let's go get them. Everybody grab that graphing calculator if you would. Let's type in the top. And all I need to know, here's the simplicity of this one, all I need to know is when you see these zeros on the x-intercept, does it cross or does it touch? That's all I'm looking for. Those are the buzzwords for this investigation. Okay, so we pretty much figured we would see one at -4. There it is. -2 and 1. Did it cross or touch at each of those? And here's, of course, what we see. It's going right on through. It's crossing, crossing, crossing. And so let's just put that it crosses at all 3. Now, watch this one. So all I'm going to really do is this piece right here, the second, and then we'll go ahead and fill in the rest. So if you're ready, let's go get that second one. Watch this. So in this case, I've got a double, x plus 3 squared and x minus 2. So watch what happens at -3 and watch what happens at 2. Here we go. Nice. And what did you notice, especially at the -3? There it is, guys. There's our 0 showing up as an x-intercept. Did you notice it comes up, it touches it right at -3. Does it go on through and cross? No. It touches and comes back. On the double, it touches. Notice on the single, though, went right on through. So what we'll do is write it as a touch at the double, into the -3, and cross there. And that's what we're going to see. So let's fill this in. Doubles. You can go ahead and graph this if you'd like. I think we've kind of played this out a little bit, though. Touches at both. We would see it touching at the 0, touching at the 4, and that's it. Would not cross. Now the triple acts a little differently, but it still crosses. So the single goes like right on through. The triple kind of levels off a little bit. We've seen this before. You know what x cubed looks like. It kind of just levels a little bit and then crosses. Whereas a single is more like this. So I'm going to actually write that. This would be a single. This would be more of like a triple. And the larger the degree on that, the more it levels before crossing. Of course, that has to be, as we will see, an odd number to do that. So anyway, not a big deal. And then I think we would kind of see a cross, touch, cross here. Alrighty, guys, you get the idea. Let's put this in and be done. Zeros with an odd multiplicity, very simply, cross the x-axis. Zeros with an even multiplicity, those doubles in particular, that's what we'll see most often, they touch the x-axis. Okay, so some good stuff as we go through this. Just looking at some of the basic theoretical graphical characteristics of polynomial functions. We've looked at zeros, we've looked at end behavior, and then we explored zeros in more detail with the multiplicities. Looks great. We'll do another investigation on the next notes worksheet and then get into some examples with this. Please let me know if you have any questions, though, along the way. And thanks a lot for listening.